Good morning, ladies and gentlemen. A warm welcome to another exciting web seminar of Composite United's web seminar series, See You Online, See You Prepared for Future. Today we have an exciting talk from Victrex on the agenda. But before we start with the presentation, I want to briefly introduce you to the structure of today's event in case you don't know yet. The first half, we will hear an exciting presentation from Gilles Larroque from Victrex. Please, during that time, keep your microphone muted, your camera turned off, so that Mr. Larroque is not disturbed. And after the presentation, which lasts about 35 minutes today, there will be plenty of time for your questions and discussions. If you have a question during the presentation, feel free to already post this in the chat, and I will read it afterwards when we start the Q&A part. Or later you can use the raise your hand button to indicate that you have a question. We will unmute you, and then you can talk to Mr. Larroque directly. That's enough for now. That's enough information for now. Now I'm very pleased to welcome Gilles Larroque from Victrex. He will give us an exciting presentation about advancements in processing of a modern thermoplastic high temperature engineered material, namely low melt PAEK. And with that, Mr. Larroque, I hand the word to you. The stage is yours. Enjoy, everyone.
Okay, thanks a lot, Bastian. So I'm sharing my screen, and I hope that you can hear me well and see me well. So I'll move to the next slide here. If there's anything wrong, let me know. So the topic today is about achieving thermoset layup speed with low melt PAEK thermoplastic tape. So I'm Gilles Larroque. I work for Victrex since about 10 years. Oops, what's going on here? So I've been I've got a mechanical engineer background, and I'm in charge of the strategic marketing activity for aerospace for Victrex. So in terms of agenda, we will have like a quick introduction about Victrex and what is A250 low melt PAEK material. Then we'll deep dive into the topic today about, oh, there's a kind of automatic, what's going on here? It was not expected. We have, so for some reason there's like automation, something moving from one slide to the other one. Okay, so it's we'll have the second part about the processing of the tape, and then a short conclusion. So the first part, what is Victrex and what do we do? So for those who knows us, Victrex invented PEEK about 40 years ago. So that's all we do at Victrex. We make PAEK material, and for those who don't know, you have the it's a Polyetheretherketone, the Polyetheretherketone family. So that's all we do at Victrex, and the main, I would say, the main material here is PEEK. So we make obviously we make polymer. We have the highest capacity in the world, about 7,000 metric tons. So we make polymer, and that's what you have here. And we make also forms. So we make filament, we make film and tape, and that's what we will discuss really today. Then we make also parts for different applications, so pipe, some medical part, and also some like gears for automotive application. And for aerospace, we make what we call loaded bracket, which is here. Then Victrex is divided into business unit. I'm part of this one, aerospace, but we have also automotive. We have energy and industrial, electronic, and also the medical business unit. So it's a global company. It's about 50 plus employees in the world, serving about 40 plus countries, and it's a FTSE 250 companies. And in terms of investment and innovation, we invest about 5-6% of the annual sales in R&D. So again, for those who don't know us or don't know PAEK, it's not new. So it's been used for maybe a couple of decades and in different applications. For instance, just for aerospace, we used to claim that about 20,000 plus aircraft have Victrex solution on board. But that's also we have a track record and history on multiple applications like automotive, energy, medical, again, electronic and manufacturing and engineering. So just to give you some real pictures about what we mean. So that's what we make more or less, like you know, the granules here for out of PAEK, but we can make also product like pipes, tape, filament, some film, and also some coating, and it's for various applications. For this one, for instance, is additive manufacturing for medical application, like a trauma plate for again medical application, a knee also, and a dental disc. And then for the rest of the industry, like this one here is a pipe for oil and gas, gears for mainly, I would say, automotive application, and again this loaded bracket here for aerospace application. So Victrex, again, is a global company. Just in terms of R&D network, we have the headquarters here in UK with what we call the Polymer Innovation Center. And then we can really develop and work on new grade, test them, etc. We have also some facility in the US, and especially here for aerospace composite part. It's based in Rhode Island. It's called Victrex Composite Solutions, where we can make parts. And then also in Asia, we have an office in Japan and in China. So really a global footprint. So now, what is PAEK? So it's classified on the high performance polymer. So this is all the polymers, and it sits on top of the pyramid here. So why we say it's a high performance polymer? Because it's really a combination, a unique combination of those properties. So when it comes to mechanical strengths, wear properties, temperature resistance, chemical resistance, for instance, hydrolysis, high purity, bioinert or biocompatible, the electrical properties, it's recyclable, and then also it can be processed. So PAEK really, if not the first one, rank really high on those key engineering requirements. And as a rule of thumb, we used to say that if you need at least 3 of them, so for instance, you want to combine mechanical strength, temperature resistance, and chemical resistance, then PAEK can play a role. So we used to say that we are replacing metal because we can cover, depending on the application, the same requirements. So it's all about lightweight solutions and also cost-saving solutions. So drilling down into the topic of today, you will hear a lot about Victrex AE250 low melt PAEK material. So that's really the new grade made by Victrex, and here it's made in a UD tape form. So to keep it simple, and apologize, I'm not a chemical engineer, but don't challenge me too much on that. But just to keep it simple, we say it's like PAEK properties with a lower melting temperature. So basically, you have the same benefits than PAEK. That's all you have here. But the main difference, and that's what you have here on the left-hand side. So the melting point of a standard PAEK is at 343 degrees Celsius. And as you can see here, for low melt PAEK, that's at 303. So we have about 40 degrees Celsius difference. So you may think it's not much, but that make a huge difference in the way of processing these based material form. In terms of glass temperature, that's about the same, and in terms of crystallinity, that's more or less the same too. So now I wanna move on to the main section of this presentation, is about the processing of the UD tape. for in-situ and out-of-autoclave application. And then you will see how we achieve high speed close to Thermoset. So to do so, I wanted to give some more background and also focus on some studies we've been managing at Victrex with partners, and dividing them into two sections. One is in situ, so there's no post-consolidation. You lay up the tape and the part is done. And then the next part, it will be about out-of-autoclave, where you have like a post-processing consolidation step. So for this one, for the in-situ, we work with, and you will see, both with Coriolis and Electro Impact, but here the first section is with Coriolis. So Victrex and Coriolis wanted to tackle the processing benefit of the Victrex 8250 UD tape for in-situ. So we set a range of parameters. We work on the speed, we work on the temperature, on the tool temp, and then we wanted to really make this part by in situ, and then evaluate the quality of the laminate. So when you look at in situ, you want to pay attention to three things. One is crystallinity, porosity, and the mechanical strength, and that's what you will see on the next slides. And also, before I start, to make it clear, when we engage with Coriolis, we wanted to know what was the reference material, what was let's say the standard, if there's one standard, the material of choice for thermoplastic UD tape. And it was kind of challenging to really set the bar, but to say, okay, use your history, use what we know. We don't want to know. So we said that's your confidential information, so we don't want to know. But tell us, when you process PAEK UD tape by in situ, where do you set the bar at the very beginning? So that's what we call the reference material, and you will see it's in gray on those graphs. So we made the panels, we analyzed them, so at different speed. That's you have the speed here on the bottom of the chart, and then we look at the crystallinity, and we want it to be around 25%. And as you can see, we were up to 20% at 20 minutes per minute, and then the crystallinity decreased. So we are really in the right range up to 15, and 20 we see the slight decrease, and then is dropping down. And the reason is because when the speed increase, you don't leave enough time to reconsolidate the laminate the right way. So the fastest you go, the less energy you have on the laminate. And then crystallinity is linked to the heating and the cooling time. So that's maybe why the crystallinity decrease. So that means somewhere the quality of the laminate decrease is getting worse when you go faster. But we've been able to achieve 25% crystallinity at 15 meters per minute, and which was kind of the already a positive result, because we were in this range at more or less 3 meters per minute. So we've been able to increase the speed by 5, and we are more or less on the same range. So positive result in terms of crystallinity. And you will see that's also the trend for the rest of the criteria. So this one was about the porosity inside the laminate. So the aerospace kind of requirements, the state of the art is like you want to be below 2%. That's the threshold. So we've been able to stay below these threshold up to 20 meters per minute. So which was pretty also positive. As I mentioned too, we try a bunch of things, and also like a thick panel. So that's the blue curve here at 56 plies, for instance, instead of 16 plies. And it was also, by the way, like a quasi-isotropic composite laminate. So the good news is kind of the thickness does not influence the porosity results. So even for a thick panel, we were more or less within the same range, and that's because of or thanks to the in-situ process. You stack up each layer. So in theory, it could be like infinite. You can lay up as many layers as you want. Of course, there's a limitation due to the tooling and the part kind of getting like you have this warping process at a certain time. But in theory, you can stack up the layers and it works pretty well. So a good outcome here, a thick or thin panel works well. And then below the 2% threshold. Again, starting from the state of the art or the reference material, we were at potentially 1.2% for a speed of 3 meters per minute. So we are more or less within the same range, again, with the speed 5-time increase. So that, again, that goes in the direction saying you can go faster and have like the same quality of results. And yeah, we did some C-scan for each panel, and the quality of the laminate was pretty good. So, and finally, so again, we might be challenged on that. It's far from maybe from being perfect. We choose ILSS, intralaminar shear stress, to evaluate the mechanical strength of the coupon. And just to maybe you know this already, but just for make sure we're on the same page, like we normalized the results, and the baseline was really the consolidated by oven consolidation coupon. So we know the best we can achieve is like via post-consolidation process. So that's the strength. Let's say this one is 100%. So as you can see here, we have a drop in terms of the mechanical resistance. To be fair, we want it to be around 80%. We are slightly below at a low speed. We ended up at 70%. And then again, when you increase the speed, the quality of the laminate is getting worse. So you have a loss in terms of mechanical strength. But we believe this can be optimized and can be pushed a little bit more on the top here and still try to reach these 80% mechanical strengths compared to an oven consolidated coupon. And back to the reference material, we started with something like 25% at a low speed. So you can see that we are more or less 2.5 times, if I can say this way, stronger, with a speed of, let's say, 6 meters per minute, so 2 times faster. So again, that goes on the direction of saying we can achieve better or at least equal quality at much higher speed. As I said too, we worked with Electro Impact, which is also a AFP machine manufacturer, and we buy in situ too, and we work on these coupon here, which is 142 plies. So as you can see, we can stack up all the plies all together, and it was processed by in situ. And here you have the C-scan on the right hand side of the microcut of this part, and there's really very low porosity, no voids, and just one here, but it's due to a splice. So the quality is also pretty good. And as you can see, we've been able to stack up many plies without kind of influencing or damaging really the quality of the panel. So pretty good results achieved here too. Just checking the time. Yeah, we are pretty good. So the next step is about out-of-autoclave and oven consolidation. So likewise, we work on this topic with Coriolis, between Victrex and Coriolis, and we set again a series of parameters, and here we wanted to push the boundaries and try to achieve high speed, high layup speed. So from a previous study with Coriolis, we set already the baseline of 60 meters per minute. That's really the head speed, again, the layup speed. And here we wanted to increase it even further. So we wanted to achieve 75 meters per minute at the same layup temp, as you can see here. And then we take the problem the other way, saying, let's look for the minimum temp we can apply. So here, you know, when you do out-of-autoclave, what you expect here is just having like a tacking kind of between each plies, each layer, because you will then consolidate it at the autoclave. So what the minimum temp to achieve this stacking laminate here, and then at what speed. And we have been able to still achieve a pretty high speed for this temperature at 54 meter per minute. So that's what we did, and we said, okay, so let's make those panels and look at them. So we made a panel, we consolidated them, and we achieved pretty good results. You can see the C-scan here. So and the microcut. So again, no voids. So very low level of porosity, close to 0%. And we achieve a crystallinity level of about 29%. So really a good laminate. And the C-scan, as you can see here, show that the part is pretty consistent. So pretty good results on that side. And again, I'm not an expert, but that's what we understand. I mean, for the AFP process, the overlap between two courses or some gaps could be a challenge sometime. But here, thanks to the flow of the material of the resin, even though sometimes if you have those, let's say, defect during the layer process, once you consolidate the laminate, you get rid of them. So it is getting very even, and you don't see them anymore. So it seems to be quite unique, and that helped a lot the processing step. So at the end of the day, that helped a lot making the part. So that's pretty a significant input here. So again, we worked also with the Electro Impact in this topic, and here we obviously it's not the same machine. So here they adapt their equipment for these high speed. And when you're processing Victrex 8250 tape at 100 meters per minute, that require an extensive manipulation of the laser power curve to maintain a constant temperature at the nib point through the entire course. So the material is processed with initial add speed, accelerating up to maximum transverse speed, and then decelerating down to cut speed. So when transitioning between a lower and higher speed, there's a third order equation that became necessary even for the flat coupons. So different curves were established for each of the first plies. So that's what you have here on these graph here. That's the power curve. Oops, hold on. I wanna maybe you see my mouse, but that's the curve on the that's the curve on the bottom left corner here. So this requires an extensive work to really adapt the temperature and the speed versus the speed. So they have also what they call the VSS, the variable spot size laser heating system. So basically you have one laser for each toe, and that's also help to control and fine tune the temperature for high speed. So this is really part of the settings of the machine before really trying to make the part. So for high speed layup, this requires further refinement to better control the feeding of the thermoplastic material on hardware intended for thermoset material to accommodate the kilting effect, the lap gap control, the coarse spread control. So these improvements created a smoother surface, resulting in a better temperature control, and increase part thickness uniformity, resulting in a higher quality laminate. So that's what you can see here. Many panels were made to fine-tune all those parameters, like for instance here, just the lap and gap control to end up with a thin surface, a smooth surface. So also some steering tests were performed, and and they were pretty promising. So it seems like again the processing of the tape, even at a high speed, was quite promising. So that's finally what we made, just for the sake of the presentation here, and for the clarity, I didn't put the video, but if you Google this, if you go on LinkedIn, you will see the video. But we've been able to achieve 100 meters per minute to make this panel here. And it was a press consolidated. I want to just highlight this. It was not at the oven here this time. Just in terms of equipment, the equipment available was a press consolidation. But for here, the focus was the layup stage, not really the optimizing the consolidation phase. But in terms, so we don't believe that would change the result. But anyway, there was no inclusion or porosity in the laminate. And as you can see here on the microcut, so we made a C-scan, a microcut, and the result was also pretty positive. So this is on the public domain. If you want to double check or have a deeper view, we issue this paper in the Composite World. So or this article, so really achieving 100 meters per minute. So that's where also you can see the video. And then very recently, we are quite happy to maybe you have seen this, but there was ChemX last October in the US, and there was a section for the award for composite excellence in the manufacturing and material and process innovation, and Electro Impact and Victrex. We submitted these findings here, and we won this award. So it's really a joint activity between Electro Impact and Victrex, and we've been able to make those panels. So by combining the high speed and also the fast cure, a fast consolidation on top of that, a fast consolidation step here. So again, if you want to have more information, it's on the internet. What I presented today is all in the public domain. So you can download, or feel free to reach out. You can download those papers. So this one done with Coriolis. It was a while ago, though. It's it has been published in 2019. We fine-tune some of the speed and some of the outcome here, but the core of the study, you can have it in this paper. And so recently here, it was published in June 2021. We have also this this paper, so between Electro Impact and Victrex again, where you have maybe much more detail in terms of the processing parameters and how to achieve these high speed. So now I'm moving on to the conclusion of the presentation. So what we wanted to highlight in this study is really that we can achieve fast layup speed. So obviously the highest one is with the out-of-autoclave. So we say we are within the range of 60 meters per minute up to 100 meters per minute. And for out-of-autoclave consolidation, and for in-situ, we can target a range between 15 and 20 meters per minute. So as you have seen, both for in-situ and out-of-autoclave, we've been able, so it was flat panels successfully made, even for thick panels. And that was not the objective of this presentation here, so we can maybe take this offline if more information are needed. But we can say, okay, it's great to go fast, but so what? So we run also some studies to quantify, because that's a key driver to address the cost savings. And based on a very specific case, it's on the door panel. We look at the cost savings by in-situ and out-of-autoclave, and we ended up with some significant cost savings for in-situ, close to 23%. That's mainly because you don't have any consumable, as you know. And for autoclave, it was only 5%, because the part was maybe too small to take advantage of the high speed. but also maybe the volume. So that's what tells us that you need to choose the right manufacturing process for the right part. But definitely we're on the right track in addressing those criteria of high speed to increase productivity and also while reducing the cost. So also, and we try to evaluate what we call the efficiency and the productivity, so the floor to floor. So this may sound pretty high. So again, happy to take this offline to give you the rationale. But when you look at those gantry machine, when you look at how many toes you can lay up in one course, that's pretty impressive. So when you combine those high capacity machines with those high speeds, then you end up with like a quite high floor to floor rate. So which is more or less between 200 and 400 kilogram an hour. So this is really in terms of the processing and the benefit of those material. But then on top of that, really you bring, and that's also what I wanted to highlight in this conclusion, that you can definitely also bring the advantage of a thermoplastic material versus Thermoset. For instance, you have no storage limitation. You have it's recyclable. It's an eco-friendly material, so solvent-free working environment, and also enables other features like the hybrid overmolding and the bonding for welding, etc. Features. So to wrap this up, if you have to keep in mind really two data points here in terms of achieving high speed. You can, for in-situ, you can achieve close to 20 meters per minute. For in-situ, and for out-of-autoclave or oven consolidation, you can achieve up to 100 meters per minute. So which is quite high compared to other material. And then, yeah, lower processing temperature and the shortage also out of autoclave oven consolidation cycle. So this is not the objective either of this presentation here, but the consolidation cycle, if there's one, also using LMPAEK, you can reduce this consolidation cycle. So to just to finally wrap this up, you have my contact detail here. And feel free to reach out if you have any question offline, and I'll be happy to try to help. And I think, yeah, that will be my last slide. So maybe it's a bit ahead of time here, but I'm heading this over to you, maybe Bastien, and if there's any question or comment.